So, as promised, things that we talked about in class, but didn't have the recorder going. So, input and output impedance. And we also have seen it before. We try to treat everything as a voltage divider, stages of a circuit. So, basically, when I hit this with a signal, it's output or its voltage above ground. So what's in between the signal and ground? So in this case, it's a resistor and a capacitor, and it doesn't matter which order they come in. Now, you want Z in to be as high as possible. And so we're trying to come up with, okay, what's a general purpose Z in? When the capacitor, any capacitor at low frequency and that's when it has its highest resistance. And as the resistance gets the frequency gets higher and higher, then the capacitor's resistance tends to go to zero, and all that's left is R. So the lowest Z in you're going to get is R, the worst case. At any other frequency, it's going to be better. And it doesn't matter what order they're in, which is the weird thing. Now, in this case, in Z in, you say, well, that's not such a big deal. But what about Z out? And remember now, Z out is with the Thevenin model. So it says, what it says here, R internal equals 0. That's our function generator. And it has some R internal, but it's basically, remember, it'll deliver the voltage you on the label for a variety of currents. And it turns out that it's designed to drive 50 ohms. So you could, for any given voltage, you could figure out the highest peak to peak you could get if you wanted to. But it's essentially an ideal EMF. But in any case, in this case, you might imagine that the Z out has something to do with the order of the two components. But again, it's not true because you add them in parallel, it doesn't matter which one is which. So when you add them in parallel, that means then you have the capacitor and the resistor, and you want Z out, to be low. So at high frequencies, then the capacitor is low, and that is basically the lowest you could get. But in worst case, then as we go to lower and lower frequencies, the capacitor's resistance, its impedance, gets so high that most of it goes to the resistor. So this is basically the worst case. So the largest possible Z you can have is R, Z out, just as the lowest possible Z in is also R. So unless you have a very specifically tailored circuit, you just say that the input impedance is R or better, and then the output impedance is R or lower. So input is R or larger, and output is R or smaller. Okay, so then we started talking about decibels. And the lead into decibels is that we know that when we these are the predictions, but we have the raw data as well. And you're covering a broad range of frequencies. And usually whenever you have something that you spot, and then the other issue is too the steps between them, right? When you're in the hundreds of hertz, and maybe every 100 is fine. When you're in the thousands, you go every 1,000, and then every 10,000. So the intervals change. And this is what logarithmic plots were made for. Now, in the case of the upper left, they're both linear. Upper right, that's logarithmic on the y-axis. So now we can see that structure because the dipping down of the resonance is so small it doesn't show up on the linear plot. And then when we go to the log-log plot, you can see that you get some straight lines. That's the other nice thing. And it spreads it out nicely. I mean, in the upper right-hand plot, we could just change the range of the axis. Maybe we'd cut off everything above 21,000. But again, the straight lines say something to us. And so then we get into the so-called bode plot, and you notice that the bode plot has two straight sections and a curved section. And this comes out of that logarithmic business, but it also, we just need to go a little bit further. So we introduced the concept of decibels. And yeah, I remember I said that bells, I don't know if it's an urban legend, but they say, oh yeah, this was developed at Bell Labs, so they call it a bell to honor that. But it's B-E-L, why not B-E-L-L? And then some people say there was somebody named that B-E-L. I invite you to check out Wikipedia. At the end of the day, decibels for everyday use is the 6 decibel level. If it's a minus 6 decibels, you've taken your signal and divided it by a half. And if you increase it by 6 decibels, you've multiplied it by 2. So the way you use it quickly and effectively is you say, okay, I have been told to have an attenuation of minus 18 decibels. And do notice that this graph starts at 0 and goes down, right? So a passive element can't go above 0. It can't amplify. It can only degrade. I didn't say that yesterday, or maybe I didn't say it that explicitly. So for us right now, we're going to be looking at minus decibels. When we get into transistors, of course, then we can have positive decibels. So 6 dB is 1/2, and if we're told we have an 18 dB reduction in signal, that means that the way to figure that out in a more accustomed way, what we think of more often, is we take 1/2 and raise it to the power of the number of dBs divided by 6. Because that's 1/2, 1/2, 1/2, so 1/2 to the third power, and we get 1/8. Similarly, if it was amplification, we'd have 2 to the third power, and that equals 8. Now, I notice that I don't have my spreadsheet here. But what we're going to do is, so this, in fact, this bode plot, as I said in class, comes from back in the day when I was a master's student. It was one of my homework problems. And so I added these legends. I can't move these legends, or these are called callouts. It's pointed to the wrong spot. It's pointing here. Now, the big deal is to see that this crossing point, that's the 3 dB point. And it's the 3 dB point is 3 decibels, which is, instead of 1/2, it's 1 over the square root of 2. So 1/2 is 0.5, and 1 over the square root of 2 is equal to 0.7071. It's the sine of 45. Ooh, cosine 45. And that has something to do with phase angles. Ooh, that's something we're going to learn more about soon. So I just set up this graph. So this line is at 3 dB. That's easy because it's a fixed number. And then this line is made so that it moves with whatever the actual 3 dB point is, the R times C. You might notice this is in radians per second. That's just omega, which is equal to 2 pi f. That's why this 2 pi RC right here, f 3 dB, and then omega 3 dB, there's no 2 pi. And so the 3 dB point is called the roll-off. So you have this nice straight line, and then you start curving, and we define the 3 dB point as when we can't ignore anymore that we may start going over Niagara Falls. And then halfway is 6 dBs, so it's hard to tell that this is halfway of the signal when it's a log-log plot. And then what's up here on the top? So decibels are defined as minus 10 times the base 10 logarithm of power out over power in. And the 10 has to do with the fact that they wanted to have the V out over V in or P out over P in equal to 1. They wanted that to be 0. And then we measure voltage peak to peak, and A stands for amplitude. Amplitude, I don't know, will it write off the page? Oh, it does. Interesting. So if we do a division, so you'd say if you have amplitude VA1 over VA2 equals 1/2 V peak to peak 1 over 1/2 V peak to peak 2, you notice that the 1/2s cancel. So if you do ratios, then you're fine. Now, power is either the voltage times the current or the current squared times R. We don't measure current, so we need V squared over R, and that's why the 10 becomes a 20. Because when you do logarithms, you see if you move the prefactor over here, it becomes an exponent. And it's to the 20th power because that's for the 10th power. If we kept this as 1, then this would be squared. So that's the consistency check. Okay, so the next video will be about how to get working on your spreadsheet. Although other videos pertaining to the spreadsheet will also have what we want to do is take our RLC spreadsheet we've already made last week, and we want to add in the decibels. All right, so that's it for now.